Newton's second law of motion tells us that the acceleration of an object depends on two things: the force acting on the object and the mass of the object. Large forces acting on small masses give rise to large accelerations, but small forces acting on large masses will lead to very small accelerations. That's only one reason not to play soccer with a bowling ball. The apparatus you will use to study the second law consists of a cart with a force sensor on board, accelerated down a straight track by a string passing over a smart pulley and attached to an accelerating weight. Now, a smart pulley sends signals to the computer about its amount of spin so that the acceleration may be determined. A free body diagram of the cart reveals two vertical forces canceling each other. That is, the downward pull of gravity on the cart is cancelled by the upward normal force of the track on the cart. There is, however, an imbalance of force in the horizontal direction, where the string causes the cart to accelerate. We will substitute different accelerating weights to change the acceleration, and then measure the force tensions in the string with the onboard force sensor. A plot of force versus acceleration should be a straight line with a slope equal to the combined mass of the cart and its load of force sensor. The experiment will be carried out twice, once with a single cart with its smaller mass, and secondly with two carts with their combined masses both accelerating. Larger mass should lead to a steeper slope in the plot of force versus acceleration. The mass of the cart and sensor is determined by setting it on its back upon the digital scale. Please note that the scale reads grams and you need kilograms. The accelerating string should be approximately 120 centimeters long and have a bowline knot loop at each end, one end to attach to the force sensor hook and the other end to the accelerating mass hook. Here is the bowline knot for those who failed to thrive in either Pathfinders or any other paramilitary group. Let Data Studio know that a smart pulley has been plugged in. Then indicate the presence of a force sensor. Set the sample rate on the force sensor to 1000 Hz and the stop time to a few seconds. Calibrate the force sensor as in last week's lab. Put in a standard value of 0.0 newtons and read from the sensor when there's no tension on the force sensor. Then input a standard value of 4.9 newtons, hang 500 grams over the pulley, and then read the second calibration force. Drag and drop the graph icon from the Displays menu to the smart pulley at the upper left, choosing to plot velocity versus time. Drag and drop the graph 1 icon onto the force icon at the upper left, so that both velocity and force are plotted with a common timescale. Use the statistics icon, shaped like the geek letter sigma. Did I say geek? And display the mean and standard deviation on the force versus time graph. Hang an appropriate mass on the end of the string. Push the start button and release the cart, allowing the mass on the end of the string to accelerate the cart down the track. Have the bumper facing forward and the end stop in place on the track so the collision at the end is springy. The top graph is velocity versus time. Highlight the straight line acceleration region and perform a linear fit. The slope of velocity versus time, as you recall, is the acceleration. Record this acceleration and its error. The bottom graph is force versus time. Highlight the region of constant force as the weight accelerates the cart, and record the mean value of force and the standard deviation as the error in force. This error should be substantial. Hang a variety of accelerating weights and repeat the measurement of acceleration and force, along with their errors. We now wish to plot force on the y-axis versus acceleration on the x-axis. Open Graphical Analysis, which will soon become your favorite graphing program because of its ease of use, and double-click on the title at the top of the X column. Change the name of the X data to acceleration with units of meters per second squared. Similarly, change the name of the y-axis column data to force with units of newtons. Input the numbers you obtained from different accelerating weights. One very annoying default of the program is to connect the dots of data with lines, resulting in a sometimes unflattering graph of dot the dot. Please get in the habit of removing these connecting lines by right-clicking on the graph and unchecking the box indicating connecting lines. There, isn't that much better? Now let's include a meaningful line, that is, the best fit straight line to the data, by performing a linear fit. Note that the larger the force, the larger the acceleration. This, of course, is Newton's second law, and the slope of this straight line should be the mass of the cart plus the force sensor that you measured earlier. Let's add error bars to our plot. From the Data menu, add a new manual column and input your acceleration errors. Revisit the X column definition by double-clicking on the title for acceleration. Indicate that errors in X values will be taken from the acceleration error column. Repeat this process to include a column of errors in your force measurements, noted as standard deviations, and change the definition of the force column to include errors from the appropriate column. Now your graph of force versus acceleration includes error bars. Does the best fit straight line fall within the error bars? Which is the larger source of error in this experiment, force or acceleration measurements? Another object undergoing the same magnitude of acceleration as the cart, but in the downward vertical direction, is the hanging accelerating mass. A free body diagram drawn on the hanging mass, with little m representing its mass, shows the upward tension in the string being overcome by the downward force of gravity. The tension in the string is the same as the apparent weight of the hanging mass. According to Newton's second law, the vector sum of these two forces should equal the mass times the vector acceleration. Assuming up means positive quantities, the apparent weight minus the actual weight equals the mass times the negative value of acceleration. Thus, apparent weight equals mg minus ma. For the heaviest weight you used, compare the apparent weight measured by the force sensor with the difference between mg and ma. Ask yourself whether the apparent weight of this downward accelerating mass is greater than or less than its actual weight. Repeat the entire experiment with two carts, but only one force sensor. Determine the total mass first, or last, it doesn't matter. Let the cart in the rear carry the force sensor and push on the cart in front. The larger mass should lead to a larger slope in your force versus acceleration graph.